Okay, we're going to look at electrical current, and electrical current is defined by the amount of charge that passes through a given amount of area per unit time. So really, if we're looking at electrical current, it's very analogous to the flow of water. The definition for the average current at any time, again, is the amount of charge. This is delta Q, which indicates change. It's really the amount of charge that flows through a particular area per unit time. The SI units are for current are amps, and again, this represents 1 coulomb per second. Very simple calculation. Here we can take a look at the average current that flows through a light bulb. In this LED light bulb, we'll say that we have 4.75 coulombs of charge that flow through it every minute. Again, we take our charge, 4.75, the amount of time, in this case 1 minute is 60 seconds, and we get an average current of 0.080 amps or 80 milliamps. Again, here's another application of this current. We have a lithium ion battery. This is a 3.7 volt battery. It can deliver 350 milliamps or 0.35 amps in 10 minutes. So basically, we're looking at what it can deliver in 10 minutes. Here's a current, how much charge will it deliver. We go again to our equation. Again, the average current is going to be 0.35 amps. We have the amount of charge divided by the time. The time is going to be 10 minutes. Convert that to SI units. 10 times 60 gives us 600. So solving for delta Q here, delta Q is equal to the current times the time. We have 0.35 amps times 600 seconds. From this battery, every 10 minutes we'll get about 210 coulombs of charge, which discharge from it. Lightning is one of the most impressive examples of the discharge of large amounts of current. We can deliver between 10,000 amps for a cloud to ground, usually when we're going from the bottom of the cloud to the ground, or as much as 200,000 amps. This is all done in a very brief amount of time, only 30 microseconds. The current is what's really dangerous to people, and that's why lightning can be potentially lethal. What's surprising is that lightning actually only kills about 80%, lightning only kills about 20% of the people that it strikes. About 80% of the people do survive it. And that's because most of the current stays on the outer part of the body, although it can create quite a bad injury. Now, if we look at this, we find that, in fact, lightning doesn't deliver very much charge despite its high current. We look at the previous equation that we derived. The amount of charge is equal to the average current times the time that it's delivered. Once again, taking 10,000 amps, multiplying it by 30 microseconds, and we get a very small amount of charge of 0.30 coulombs. It's less than the battery example that we did. Even at maximum, when we're taking a very, very large current for lightning, at 30 microseconds, we're only delivering about 6 coulombs. Again, we've got to remember that lightning is delivering this charge at a very, very high voltage. So even though the amount of charge isn't all that great, the voltage, which is the amount of energy per unit charge, is high, and again, that can make lightning quite destructive. Looking at the instantaneous current, like many of our quantities, we can do an average over time, or we can say what is happening right now. The instantaneous current just goes by the limit where the incremental time is going to 0, where we're looking at how much charge per unit time is flowing. So it's a rate of charge, how much charge is passing through a particular cross-sectional area at any given time. Now, with electric current, if we have positive carriers, which we can have in some cases, if we have ions that are positively charged and they're carrying the electricity, the current flows in the direction that the positive charge carriers are going. So we define current as being hypothetically what direction positive charge would go. However, most of our conductors have free electrons, and the free electrons are carrying the electricity. They're the ones doing the work. So whereas in an electric field, the positive charges will go with the current, the negative charges actually move against the current. Here's an example of a very simple circuit. We have a battery, a switch, and a light. We have the representatives of, or a representation of these. Here we have the battery represented by these unequal parallel lines. We have the lamp itself represented by this symbol right here. And again, you can see why we call it a circuit, that the electricity is going to have to go around and return to its origin. It originates from the positive terminal of the battery, flows through the lamp, then returns to the battery again via the negative terminal. Again, circuits, name circuit implies circular motion where electricity returns to its source. Many of the ways that we characterize a circuit is in terms of current and voltage and also resistance. We'll talk about that later. Now here is what a just general representation, a drawing, would be of a battery hooked up to a resistor, and an ammeter is placed here to measure current. A voltmeter is placed across the battery or the resistor to measure voltage. So in measuring current, we use an ammeter. It tells us how many amps are flowing through a particular object. So current is through. For a voltmeter, we talk about across. What is the potential difference for the charge to cross from one terminal to another, or from one side to the other? Okay, so voltage is always measured across, current is always measured through. We can simplify this diagram so we don't have to draw everything out by making the battery again represented by these unequal parallel lines. The voltmeter can be represented by the circle with a V to indicate voltage. The ammeter can be represented by a circle with an A. So many times when we're using meters to measure the characteristics of circuits, we'll use a circle to represent that particular meter, and then whatever symbol to represent what we're actually measuring. Voltage or current, amps meaning current. I'll also notice that the resistor has these sawtooth, has a sawtooth pattern right here. Again, here's that same setup again. Now we've replaced it with a light bulb. Our battery, we're actually using two batteries in series to boost the voltage. So again, we can measure the voltage across, and we measure the current through. Again, if we follow the current, it's going to go from the battery, through the light bulb, through the ammeter, and then back to the battery. So current is through, voltage across. Once again, just to emphasize this, if we have positive charge carriers, the current goes with the motion of the positive charges. Remember, when we have an electric field, the electric field represents the force per unit charge that we have. So the electric field always points in the direction of the force on the positive charged particles. Again, most reality is that we're going to have free electrons carrying the charge. Therefore, what is going to happen here is the negative charges are going to move in the opposite direction of the electric field. Remember, positive charges move with the electric field, negative charges like to move against the electric field. The electric field points in the direction of the current, so the negative charges move in the opposite directions.